this model, and this model. So in ST3131 or ST3132 mathematical statistics, you learn a simple model. Y1 to Yn comes from the normal distribution. Here we are dealing with a slightly more complicated model. Our Yi is the simple linear regression model, and that is the distribution. And all the Yi are assumed to be independent, just like the simpler. So for this simple case, we can show this. We can show that this is as a T distribution with n minus 1 degrees of freedom. Now for the more complicated simple linear regression model, we can show that this statistics, beta 1 hat minus beta 1 0 follows the T distribution with n minus 2. So that's the difference. The difference is we're dealing with a more complicated model. So once you understand the distributional theory, you can do tests on. So here, you can do tests on mu, for example. Same thing we are doing here. So we are testing whether beta 1 is 1, 0 or not. And so this linear model theory will be explained in greater detail in chapter 3. Here I just state. Yeah. So once you know the distribution, you can construct confidence interval. There's a standard method for constructing confidence interval. Once you know the theory, once you know the distribution, so you can do this too. 3 and 4 easily. So that's what we did in the last lecture. And for regression to be useful in practice, you need to be able to test a data set, right? And R has two functions. One is called summary. One is called confidence interval. For you to do testing and construct confidence interval. You can also show that this statistics, which is a slightly different one, but it also has n minus 2 degrees of freedom. And according to linear model theory, after that, you can construct confidence interval and do testing. So if you have forgotten this, I'd like you to go back and revise your mathematical your statistical theory, okay? Because we follow the same approach to testing and confidence interval. It's not anything new. It's just that we are dealing with a more complicated model, slightly more. What model is that? Simple linear regression model. Okay, that's all. So, when we test beta 1 to 0, we're testing for a linear component. Is there any linear component in the relationship? Yeah? So, you can do that. Here, I have also tried to do it by hand for you. I mean, not by hand, but to do it, not using any function, but to go through some you might want to try this. Instead of relying on the two functions to get your confidence interval. So, of course, we also learned the use of p-value, right? So, for example, when we are testing whether beta 1 is 0 or not, it's not 0, so this is this beta 1 0. It's a constant that we are trying to test. Well, the p statistics is given by this, and the p-value is this. So p-value is very small, so we reject the null hypothesis. And so there is a very strong evidence that this slope here is not 0. And this was testing the slope. This is beta 1. Now, if you want to test beta naught, well, you can use this p-value. This one is even smaller. It's almost 0. You cannot even compute it. You just say it's less than 2 to the power minus 16. Yeah. Obviously, the intercept is not 0 in this case. So, well, if you use the complete function, you can construct confidence interval for beta 1 and also for beta naught. So, try to here I use this I derive it using the formula itself and not relying on any function. Okay, so I am done with hypothesis testing and confidence interval for simple linear regression. Next, I want to talk about a very important concept in regression, which is called the analysis of variance. Now, so what is variance? Variance measures the spread of your observation. So, let's say you measure y1, x1, y2, x2, and so on. Let's say you measure all this. And yeah, for example, take a simple example. Let's say X is the year after graduation, number of years after graduation. Y1 is the monthly income or the monthly salary of that person. So X I can fix it to be 0, that is just graduated. Or I can fix it to be 5 years down the road. Or 10 years. Yeah? And I can measure the what? The monthly salary based on the X that I fixed. So I can choose 10 people who just graduated, another 10 they graduated for 5 years already, and then another 10, graduated 10 years. And then I measure their, I ask them, what is your monthly salary? Yeah? Suppose I'm able to get that information. So I have 30 data points. So now the question is, do you expect all of these monthly salary, Y1, Y2 up to 530, will they be approximately the same? Yes or no? Definitely not, right? I mean, you just graduate. Don't expect people to pay you 10,000, right? And after 10 years, don't expect people to pay you 4,004, right? That's the starting salary, I will agree. If you still accept 4,004, you're an idiot. Yeah? Or you have no ambition. You got bullied. That's what happened. So you must have high pay when you have graduated 10 years down the road. Unless you want to go and go for dishwashing. Huh? No matter what is your year of graduation, your pay will still 2,000 to 3,000. That's why I found, I go around, I go shopping. I'm interested to do dishwashing. And after I retire from MBA, the pay is about 2,000 to 3,000. I don't know whether I can take the job or not because it's quite hard, I don't know whether I can even sit down or not. I will wash dishes for 8 hours straight. I think I'll die. But if I collect that data, dishwashing, and their education background, how many years have they graduated from the university? I expect the response Y to be pretty constant, right? After 10 years, 5 years, 0 year, it doesn't matter because when they hire you, they don't look at your certificate. Yeah? Oh, you score A in Dr. Gan's regression analysis, huh? Okay, I'll hire you to be a dishwasher and you get extra pay, 1,000 more. Will that happen? Just because you did well in my course? No, unless I'm the boss. Then I will give you $1,000 more. You did well in my course. So you can see that this variation will be approximately constant, fluctuate around 2,000 to 3,000. So, is there any variation? Very little. So I'm talking about the variation of this. I'm talking about the variation of the response. So let's go back to the more sensible example, where X is the year after graduation, number of years after graduation. I'm sure there is a variation. So now, we want to analyze this variation. Okay? And this total variation is called SST. SST is the corrected variation in Y. I've explained what is corrected, right? So SST, the total variation in Y, is this quantity here. Right here. So that's called corrected. I've corrected using the mean. So this is called, in fact, this, you might recognize that this is just part of the sample variance, right? Well, sample variance is a measure of variation. If you take away the coefficient 1 over n minus 1, it's also a measure of variation. So there's some variation. And this SST can be decomposed into two parts. One part is called SS residue, and one part is called SSR. And that equation is here. This, which one is SSR? This is SSR. So let me, the order is slightly off, but this is SS residue. So let me move it up. So let's take a look. So what we have is we have this SST, the total variation in Y. We try to understand why is there a variation in Y? Can we somehow explain why? See, for the dishwasher job, that data set, there's no variation or very little variation. We know why. Yeah, because it's not related to the number of years you graduated from university. Now, you can decompose this into two variations. Again, both are variants in some way. And the one that I've written on the right hand side there is called sum of square of the residue. See, yi is the observed value. This is the observed value. This is the fitted value on the line. So the distance from the observed point to the line is the residue. It's a measure of the error. So I square, I sum it, I get the sum of square of all the residue. And the other part, I call it SSR. I call it sum of square of regression, which we actually prove that this SSR also follow another formula. It's delta 1 hat times SX1. We proved that earlier, right? And so, can you show this equation? Well, do it at home. Make sure you can. I don't think it's very easy. Neither is hard. So if I display an equation without showing you the proof, what does that mean? That means I expect you to prove it yourself. Alright? Why? Well, very simple reason. You're adults already. You have to prove it yourself. And when you prove it, you learn something. Okay, so now, in the process of trying to understand the variation in Y, we are able to decompose the total variation into two variations. One is residue. The other one, we call it sum of square due to regression. How do we interpret this equation? So I will not go to the proof. You can prove it either in tutorial or on your own. It's not in tutorial. So now I want to try to explain the significance of this decomposition. What does it mean? Well, let's look at a case. Let's look at case 1. In case 1, I have x on the horizontal axis. I have y here. So this is my response. And this is the data that I collected. Yeah? So if you look at y, this is the value of y1. Maybe y1 may not correspond to this. So this is the value of another y. This is the value of another y. So you can see there's variation in y. So the question is, why should there be a variation in y? Can we explain it? Well, we can. We can actually explain it. See, when I plot it, I find that they all fall on a straight line. That means what? That means as x increases, y follows. So y is related to x. And suddenly it follows x. The relationship is perfect. They all fall on a straight line. So what is the residue for this point? yi is here, yi hat is here, so it's 0. So what's the residue here? 0. So the sum of square of residue, yeah, this one is 0. So what can you say? Well, then I know variation in y, the total variation in y, cannot be explained by the regression line. So this, I now know this sum of square of the total variation in y can be explained by the regression line. It follows a perfect relationship. SS residue is 0. So the regression line explains why there is such a variation. Yeah. So now let's look at the second case. Case 1 probably will not appear in practice because you are not going to find a data set where the points fall on a line perfectly. It's only in the world of mathematics you can do it. This is more likely scenario. So you collect the data. X could be the year after graduation. Y is your monthly salary. It has to go up. Whether it's linear or not, I do not know. It could be a curve. Yeah? But it has to be an increasing trend. So I know when I collect this data, I see that all the y's are actually different from each other. And I know it must have something to do with x. Yeah? And the residue is here. This is a negative residue. This is a positive residue. Yi minus this. Yi minus this. So this is a negative residue. This is almost 0. Negative, positive, negative. So in this case, the sum of square of residue will be small. So it's yeah. You can see that the sum of square of residue is small. So what does that mean? That means SSR has to be large. So let me write down the equation. SST is SS regression plus SS residue. So if SS residue is small, then SSR has to be large. Because SST is a constant, given that data set is constant. It's just that who contribute more to that variation in y? Is it the residual part or is it the regression? So now we have a case where SS residue is small, SSR will be large. And so if you look at this ratio, SSR over SS residue, you find that this ratio will be large because the numerator is large, denominator is small, so you have a large ratio. Or you can also interpret this as what? The variation in y, most of it, I think the key word is here, most of it, is contributed by the regression line. So why varies? Because there is a strong relationship with x. That's why there's a variation in y. And because of that, the sum of square residue is small, and you have a large SSR. So that's how you can interpret this line. So let's move on to another case. This is a case where, X is the number of years after you graduated from a university. This is the monthly salary they'll pay you when you go for this washing job. Whether it's 0 year, 5 year, 10 year, I think it's not going to change. It depends on how fast you can wash the dishes. Yeah? It's not, hey, how many A's you got in in your certificate, right? If I go for this job, I'm afraid they'll give me a low pay. Why? Because my action and reaction are very slow now. I move slowly. Why? Because I'm an old man. Huh? You go for this job, you'll be here. Congratulations. I'll be here. But don't be too happy. You're 3,000, I'm 2,000. We are about the same. Huh? So, if there's no relationship, then what happens? So let's write down this equation again. SST is SSR plus SS residue. So in this case, SS residue will be large. There will be a large variation. Because they are not going to follow any regression line. There's no relationship. So it's going to be large. And so SSR will be small, and then this will be small. So this is an example where we can, the variation cannot be explained by the regression line because this is small. It's all residues, it's all error, random error. Huh? So in other words, this regression line contribute very little to the variation involved. So what's the purpose of that analysis of variance? So what I've gone through is called analysis of variance. The three variances, the relative sizes. Sum of square total, remember, is a constant for a given data set. What can be small or big will be the sum of square of residue and the sum of square of regression. So if we want to test this one, beta 1 equal to 0 versus beta 1 not equal to 0, then we can use this ratio to test, right? Because we already learned from the argument that I gave you earlier. If we have a strong relationship, then this will be small, this will be large. Small, this will be large. So if you have a large ratio, then it shows that it gives us evidence that beta 1 is not equal to 0. You got that? So on the other hand, if you have this is large, no relationship, then this will be small. So if the ratio is small, then you do not reject H0. Maybe H0 is true. Maybe there's no relationship. So we use it. We use the ratio. But this ratio is not good. Why? This ratio is not good for you. Why? Anyone? Why is that so? Can anybody think of a reason why this ratio is not good? The logic is good. But we cannot use this ratio because we don't know the distribution of these statistics, this ratio. However, we know the distribution of these. If you divide SSR by 1, the degrees of freedom for SS regression, and n minus 2 for sum of square residue, you can show that this statistics follows an F distribution. So instead of using this ratio, we use this ratio. Because in linear model theory, you can derive the distribution of F. And that's what we are going to do in the next chapter. Introduce this theory. In fact, last semester I set a problem on linear model theory to show all this. Unfortunately, very few students got it because they don't believe in linear model theory. Well, I hope you believe it. Well, so we will then reject H0 if the test statistics is large. Yeah? Or you can use p-value for that matter. And this decomposition of variance can be summarized using a table. Here, usually we write out as a table. This table summarizes the decomposition of the variance. What decomposition am I talking about? This one. This equation shows the decomposition of the total variation in Y. And so we usually summarize this decomposition as a table. And we show the different variances. Sum of square is the variance. So here's a regression, residual, total. And then the degrees of freedom, 1. N minus 2. You know, for simple normal model, y bar minus mu the other bar, put s over root n, is t with n minus 1 degree of freedom, right? Here is n minus 2. For the testing of this is 1. So all this can be derived using linear model theory. And then after that, you divide this by this to get the fs, and then in R, they will also give you the p-value for testing. So that's the idea. Now this idea of analysis of variance table, I'm sure you will come across it many times when you take another course called experimental design. And when you take that course, you will then realize that experimental design and linear regression, they share the same theory. Okay? But that's later. So for analysis of variance table, you can use these two R functions to get the table. So this table actually eventually allows us to test for what? Test whether the slope beta 1 is 0 or not. That's what it is. So example. So in this example, I have already fitted a model, right? I fitted a model, and now if you do not know what I mean now, fitted a model, you go and look at my earlier statement. So actually, it just means what? Lm. I must have just show you Lm x, and then assign to fitted model. So I want the ANOVA table. So I use summary dot AOV to get the table. See, here's the source. Total is not displayed here. It's okay because we don't need it. Degree of freedom, sum of square, mean square. F value is the ratio of these two. Then that's the p value. And then here, 3 little stars means highly significant. Yeah, 2 stars means somewhat significant, and so on. So that's what it means. Significant quotes. In case you do not know, that's how I use it. And analysis of variance table can also be derived using this. This one. You can use this function ANOVA to extract this ANOVA table. And this is what we use to test this. It's not equal to 0. So what do you do? you always reject H naught if the p-value is small. There's only one way to do test using p-value. You reject the null hypothesis when p-value is small. Okay? So here, p-value is very small. We reject H naught and conclude that there is very, very strong evidence. There is a relationship between X and Y. And then there is, I don't know whether you studied this or not, when you study the normal model, the simple model that I showed you. You can do an F-test or a T-test, and they are equivalent. So the T-test is what? Beta 1 hat minus 0 over the standard error of beta 1 hat. And then you take T squared. T squared, so you get this. Standard error is this one. And then simplify it. You find that it is an F. So this is the proof that you can either use t-test or the f-test. Because earlier, so here I'm using f-test to do this test, right? But earlier, let me go back a little to show you when. Earlier, right at the beginning of the lecture, I talk about this case, right? I talk about this case, this one, and I use a t statistics. It's a t. So to test this beta 1 equal to 0 or not, you can use this t-test, or you can use the f-test from the analysis of variance table, commonly called ANOVA. So either one will work because they are equivalent. Yeah. So let's do B. Let's go back to the beginning. Let's go back to the beginning. What happened? So today, my main focus is to talk about this analysis of variance, in which we decompose the sum of square of the total variation in Y into two variances. One is the sum of square due to the residue. The other part is sum of square due to regressions. If sum of square of residue is small, then it indicates that this variation in Y can be explained by the linear regression model. If the sum of square of residue is large, that means this variation in Y cannot be explained by or very little of it can be explained by the regression model. So that's one. And then I show that there is an equivalent. So let's take 5 minutes break. And then we continue. I still hear a lot of talking. Okay, thank you. Now, next I'd like to talk about testing and confidence interval for sigma square. And then I want to talk about confidence interval for the mean response at a particular regressor value prediction. So one main purpose of regression is to do a prediction. If we have an X, you don't know what's the Y until you measure it, right? You can use that to predict. And then coefficient of determination. Now, this first one, actually it's also related to what you learned earlier. So for let's go back to the simple model, simple distribution that you learned in an elementary module. N minus 1 sigma squared over S squared is chi-squared with n minus 1 degrees of freedom. Yeah? So here, our objective is to test sigma squared, or to construct confidence interval for sigma squared. And for this simple model, we know that you can derive it that this n minus 1 sigma squared over S squared has a chi-square distribution with n minus 1 degrees of freedom. So what about the simple linear regression model that we are talking about here? So again, our distribution comes from this assumption. So in order to construct confidence interval for the variance of this error called sigma squared, you need to make this assumption that epsilons are normally distributed and independently distributed. It's because of this, that's why the responses are independently distributed. They are not related. So you can see that this quantity follows a chi-square distribution with n minus 2 degrees of freedom according to linear model theory again. So if you compare this expression with this one that I've written down, you see the similarity. Yeah? So this is what you learn in, I don't know, ST3132 or ST131. When I taught ST131, I show the student this equation. So here we have a different model. Instead of a simple normal population, we have a simple linear regression model. And so the expression, although they look similar, but they are slightly different, as you can see. The main difference here is, did I do anything wrong? Sigma squared over S squared, I think. Sigma squared, I think I got something wrong. I think it should be S squared. These two got to follow. It can't be different. Okay, now they look more like it. Yeah? Where mean square residue is the estimate of sigma squared. So it's the same. So this quantity is the estimate of sigma squared. I think I moved too much. So what happened now is we know the distribution. We can then do testing, or we can construct confidence interval for it. So that's what happened. All right. Now let's see. Well, let's look at an example. The rocket propellant data. So we have the data set. I've given you the R program. You can also do this test. And for those who are, again, learning R for the first time, try to do it by hand. Try to calculate all this instead of relying on some R function. So here is just a basic application of the formula using the data from this rocket propellant data. And then you can find a confidence interval for sigma square. So this R program here will show you how you can do it by hand. So to do it by hand, you will do it using the chi-squared percentile. The function is Q, CHI, SQ, and so on. And this is how you can extract the mean square residue from the ANOVA table. Yeah. Where's the? Now let me just show you where is the mean square residue. This one. This is. Oh, I think I moved already. Can you go back? So this part here. This is mean square residue. Okay? It's the sum of square divided by 80. And you can extract it from the table using this extractor. And then you can construct confidence interval for it. Okay, so that's all I want to talk about this estimation of sigma square. Now this sigma square is a very important quantity in regression. I will talk more about it later. Now, the next one that I want to talk about is the estimation of the mean of response at a particular x0 value. So here is the regression line. Suppose we are interested at this x0, and this particular point here is the expected value of the response at the point x0. And that value, of course, is also the predicted value, or you call it the fitted value. There are many versions, many ways to call it, but they are all the same. So that point on this point on the line here is called the fitted value or the predicted value. And that point also happens to be the mean of the response of y at the point x0. So what we want to do now is to try to estimate this quantity. So can you tell me, just casually, this expectation of y given x0, is this a constant or not? Or is it a random variable? Yeah. If you think it's a random variable, well, your earlier education was wasted. All that education was wasted. Expectation is not a constant. It is a constant. Sorry, my education also wasted. Let me just say carefully. Expectation of y given x0 is not a random variable. It is a constant. All right. We want to estimate this mean response at a particular x0. So what does that mean? For example, x0 is 5 years after graduation. I want to know what is the average salary, monthly salary of graduates, of people who graduated 5 years from a university. I want to know the mean. You got that? After 5 years, some will be low, some will be high. But I want to know what is the overall average. And this is what it is. Expectation of y given x naught. So this is an important quantity that is of interest to practitioners. So let's see how we can do it. Well, the equation y is beta naught plus beta 1 x plus okay, this y naught, this x naught, this epsilon naught. As I have said, epsilon naught is a random variable. So y naught is also a random variable. If you take expectation, you will get this, which is this. So here I'm just trying to emphasize that I take expectation of y given x naught. Okay, it's the same. Whether I put x naught there or not, I'm doing the same thing. I'm trying to find the overall mean of the response given x naught. So as you can see, the expectation is just a function of beta naught, beta 1, and x naught. They are all constant. And I'm going to estimate it. To estimate, for statisticians, we just put a hat there. So it means it's an estimate. So I have two notations. I can also use mu as my mean of y given x naught. So in order to estimate this, I estimate beta naught using beta naught hat and beta 1 using beta 1 hat. So you see, if I want to construct confidence interval for this, I must know the estimator, I must know the variance, and I must know the distribution. That's what I'm looking at. So the next step is for me to find the variance. The variance. So take the variance of this. This is variance of two quantities. So you learned earlier in statistics that if you take the variance of this, your variance of beta naught, and then plus variance of this, plus the covariance. Yeah? And I think I've skipped a number of steps here already. So I actually would like you to go through the proving to come to this. Yeah? So you can see I actually expect you to do quite a bit of proving on your own. And as you continue, you will find that, it's not difficult at all. So, I have skipped many steps, but what I want to show you is this is the final outcome. So the variance of y at x naught is this, and it depends on how far it is from the center of x bar. What does that mean? Look at this. So the derivation is important, but this final result is also important. See, we want to measure we want to estimate the mean of y at a particular value of x naught. Now, if x naught is exactly at the center of the x value, then the variance will be the smallest, right? But if your x value is far from the center, then it says from this formula, we know that the variance will be large. The larger the difference, the larger is the variance. So what that means is, if I collected a data set, year of graduation out from school, 0 to 10, and then if I the mean is about 5. So if I want to find the variance of the response for 10, it will be harder. But if I harder in the sense that it will be less accurate because the variance is large. But if I try to estimate the variance for x not equal to 5, then I probably will feel better because the variance is going to be the smallest, it will be most accurate. All right? And okay, so we have the estimator, we have the variance, and we also know that this is normally distributed. Why? Because it is a linear combination. So, if your estimator is a linear combination of y, and all the y's are normally distributed, then it must be normal. This is something, again, you prove in statistical theory. So we are using this fact here. Now, next is this estimator minus the parameter that we want to estimate divided by the standard error of the estimator has a t-distribution with n minus 2 degrees of freedom. Now, this comes from linear model theory. Again, I do not want to explain it here because when you go to tree or multiple linear regression, you will learn that this is true. So once we know you have the the estimator, you have the variance, you have the distribution, then you can construct confidence interval based on this result here. Now, as long as you have the distribution, you can derive this. Again, I expect students to fill in the blank by derive this confidence interval. Why? Because this is what you learned earlier in more elementary statistics courses. So I don't want to go through things that you have already learned. This is very simple. This step is simple. Make sure you know it. Then for the rocket propellant data, basically here is just to show you how you can apply to a data set. Substitute all the values. It's not too exciting, but it will show you confidence interval for this. Now, look at this statement. I set this from the textbook. I got a number of pages from the textbook because I'm too lazy to keep it. Some students say, I cannot search your notes now or something. Control F. Yes, you cannot search because it's a printout. Too bad. You cannot search. I know. So why do you have to search? I want you to understand every piece. Don't search. Just read everything. Now look at this. It says the mean response of y given x not equal to this is between this and that. I tell you, this statement is very dangerous. This is not a true statement. Sometimes when you read a book, you have to be careful. Does it mean when you construct confidence interval, the true parameter that you want to estimate is now confirmed to be between 2086 and 2176? Is that what happens? You don't know. We will never know whether this one is between these two values. Why? Because this is a confidence interval. Confidence interval says we are 95% confident Are we constructing 95% okay or what? 95% confident that this value lies between this and this. Well, it may not lie inside there, right? So be careful. This is written this way. The confidence interval is summarized this way, very casually. But this is not what it meant. You cannot just read it and say, yes, this parameter is between this and that. That is called what? Mathematics. This is not mathematics. This is statistics. So I want you all to be careful with some of the notation used in the textbook. It doesn't mean what it says. Do you get what I'm saying? Because this is a confidence interval. All right. So how do you construct confidence interval for the mean response of y and x not equal to x bar? I'll change it up slightly if you have downloaded the earlier version. Whenever I see anything error or what, I revise my notes. So please check canvas for revision. If you don't know what I revise, it's okay because it doesn't affect you. Alright? So if you know what I revise, then you know. So, very easy. I want to find the mean response at this, so I assign mean x to this. Then I create a new data frame. Think of it as a data set. Data frame is a data set, or new data. And then predict. Use this R function. This is the filter model. This is the new data. This is the x naught value that I need to put in. And I'm going to construct confidence interval for 95% confidence interval. Got it? So it's quite simple to use that. Now this course is about, partly application, partly theory. You need to know how to do all this, so that when you go out to work next time, you can fill a line, you can do prediction. Here I've done it 2 ways. I have also done it, by using all the formulas that I've shown you. Or I can use this function directly. So you can do it the hard way. For learners only, but once you are good at it, then you can just use this function directly. So this part and this bottom part, they are the same. They are doing exactly the same thing. But this is for you to learn how to manipulate the data a little bit. Yeah? If you are not familiar how, I suggest you go through this part instead of going to this part. This part is after you have learned. Alright, so what happens now is so here's the output there. So I'm just going to look at the function, this one. So if I do that, then it will give me the filter value, the predicted value, the estimated value, the lower bound and the upper bound for the confidence. Or you can find confidence interval for all x naught using this function. If you don't provide a particular x naught value, it will just give you all. Alright, and so it's summarized here, the same thing. And you can draw. You can have, at each point you have a lower and upper bound, you can join them together, and then you get what is called the confidence band. Huh? So it gives you a confidence band of the mean value of y for different x. I really like to finish this today, so let's go on and talk about prediction. Now to estimate the mean response of y at a particular x value is important. For example, I want to know what is the average salary, monthly salary of people who graduated 5 years from now. But prediction is also very important. Okay, let's say I meet someone. I say, how many years have you graduated? 5 years. Or 6 years, let's say 6 years. My data set has 0, 5, 10. So I met this guy 6 years. I just need to know how many years he has graduated. And then I can make a prediction of how much his monthly salary is based on the model I picked. So this is one use of linear regression. Well, how do we do it? Again, I've revised the note to add in this in case you have not noticed. You need epsilon naught there. So, this guy whom I met graduated 6 years from school. I don't know his monthly salary. I want to do a prediction. And I'm not going to ask him for his monthly salary. So his monthly salary is actually called a future observation. I'm not measuring it. It's an observation that I would like to know, but I'm not measuring. So it's a future observation. Now, of course I can use my model, put in 6 here, and then I can estimate this person's monthly salary. Okay? So that's what I can do. I have an estimate, but what I really want is to be able to construct confidence interval to track his monthly salary. Now, in order to do that, we need to know 3 things. 1, estimate what it is. 2, the variance. 3, the distribution of the statistics. Well, here we use this. We use this quantity, y0 minus y0. Now this quantity, this is the future observation. This is what I predicted, what I think is how monthly salary is based on my model. And so I'm going to use this to help me to find the confidence, the variance, and hence the confidence interval. So I need to find the variance of this. Now, variance of this is variance of y0, which is sigma squared. The variance of this is this. This is the variance of the mean response, which I have shown you already, just shown you. Yeah? And then variance of this, first one, variance of this, and then there's a covariance term, right? Covariance of y0 and y0 hat. Now what's covariance of y0 and y0 hat? Y0 hat is actual monthly salary. Y0 hat is the predicted. Well, these two quantities, the covariance is 0 because the future observation is independent of how I estimate this monthly salary. You get that? It's a random variable. It has to be independent from my prediction. So there is a part here, the covariance of y0, y0 and y0 hat, which is 0. So after that, you can then construct confidence interval based on this variance. Now, if you compare this with the previous confidence interval, this is the same, this is the same, this is the same. So the confidence interval for mean response and predicted future predicted value, they are similar except for this. Now the one here means what? The one here means when you construct this confidence interval for a future observation, the interval is wider. Okay, this is not a confidence interval, this is a prediction interval. Because of the one is wider. In other words, it's harder, it's easier if you want to estimate a constant. To predict a random variable is harder, and there will be more variability. Okay, that's what it is. So you can refer to the rocket propellant data and then calculate it. And then, as I warned you before, this statement is not totally true. Technically, it's not true. Because this says the future observation of this person 6 years after graduation is between 2048 and 2046. This is definitely not true. Yeah? The guy could be earning $1 million. Okay? So, this just a very casual way of writing, saying that I predict that is the future observation for regressor with x0 value is between this and this. Predict to be between these two boundaries. Whether it will fall inside or not, I don't know. Yeah? It could be outside, but at least we know, we have some idea that it's probably between here. So be very careful with all this very casual notation in the text. Yeah? So how do you construct confidence interval or prediction interval using R? Again, you create data frame. Suppose you want to make a prediction for x0 equal to n. So this is an arrow. You can either write x, for those who are learning R, you can write x0 equal to n, or you say, those are arrows. This and this. So, create a data frame and use it. So what happens now is you are using the same function, but now say I'm going to do a prediction. To do that, then one will be added into the calculation. This one. Okay. Then that's what happens. It's very simple. You can check that this interval is larger than usual. Okay? And okay, so I guess that's all I want to say. So let me just put a summary of what we've done today. So on the second part of the lecture. So first of all, we learned confidence interval for sigma squared, the mean response at x0, and then the prediction of new observations x0. So this